in this demonstration, we are going to demonstrate the glycohemoglobin procedure. So inside of this is actually little resin beads that will bind, or the non-glycated hemoglobin. So the first thing we have to do is we have our standards and our controls, and you also have patient samples. And this is a whole blood sample, and what we're actually going to do is we're going to lyse it so that we free that hemoglobin that's inside of the red blood cells. So you're going to pipette 500 microliters of our glycohemoglobin lysing reagent to each of our tubes. And I've already gone ahead and pre-labeled all of my tubes for this procedure. So I have one that's labeled with each sample as well as lysate, and that's what I'm pipetting this into. I made sure I overly labeled so that way there wasn't any confusion, because otherwise you're going to end up with 4 sets of tubes that all have the same label on it. All right, so 500 microliters of our lysing reagent, and then we're going to add 100 microliters of each of our samples. So let me go ahead and set this. You remember that you always want to store these at their highest volume, so they're not under stress in storage. So I've got my standard, which has a 10% glycated hemoglobin concentration. And glycated hemoglobin and hemoglobin A1C, they're not one. Glycated hemoglobin takes into account all the fractions, which is A, B, and C. And that's what that 10% is. Your hemoglobin A1C is actually a smaller subset of that. It's the largest subset, but a smaller subset. So when you're doing your calculations, you can either do it based on the total glycated hemoglobin or the hemoglobin A1C. And these will be aliquoted out for you instead of in the manufacturer's vials. These actually come as dried reagents, and we reconstitute them with water. And then we're going to vortex them. We're going to let them incubate. Make sure I put them back in the right spot. We're going to let them incubate for 5 minutes so that we can fully lyse all these red blood cells to free the hemoglobin. And I'll see you when we're ready to continue with the procedure. Okay, so the timer just went off, so this is now hemolyzed. So we've labeled some tubes with hemoglobin A1C on there. And what we're next going to do is pipette our resin in here, and there are little beads in here. So even though it looks like a homogeneous solution, we are going to invert it several times before we pipette. Oh, you can actually see the beads in it if you look closely. That's fun. Now, it may be really tempting at this point to just go right back into the bottle, but control yourself. Take the time to recap. Invert it again. And then repeat. All right, so I finished pipetting the resin. Make sure they're, kind of do a visual check, make sure they're all kind of at the same height, because we are diluting the sample into this resin, so it does matter how much volume's in there. So next we are going to transfer 100 microliters of our well-mixed homolysate to each of these tubes, and I am just going to make sure that I am not making any mistakes in terms of which one's going in which. fun part. So to make sure it's homogeneous. And then we're gonna take these cool plungers, stoppers. They actually have a little membrane at the end of it, and this will actually separate the beads from the hemoglobin A1C, or glycated hemoglobin. So what we're gonna do is we're gonna push this in. We're gonna give about a centimeter between the surface of the liquid and the bottom of the rubber stopper, because we want space for it to be able to mix. And my general rule is my pinky is about 1 centimeter. That's how I kind of guesstimate it. And this membrane is enough that you could just mix it like this, and we're gonna mix it for 5 minutes by hand. Like so. Pretend you're a hematology rocker. And you can trade off with your partner for this. All right, it's been 5 minutes. I'm not gonna lie, my wrist hurts. Okay, so it's well mixed. At this point, the resin has bound to the non-glycated hemoglobin, and all the glycated hemoglobin is currently free floating. So when we push down this stopper, the glycated hemoglobin is going to come up into this little top tube. And the key thing with this is this membrane can pop. And if it pops, the beads come up into the supernatant and it cannot be rescued. You will get an extremely high absorbance and you'll get no results. So be very careful and only push it down as much as you actually need to. And another thing to note is that we are not throwing away our homolysate because we need it for an additional step later on. So don't throw anything away. All right, so here we go. Gently but firmly push. When you start getting a lot of resistance, that's when you should probably stop, because we only need 100 microliters. So about when I think I have at least 100 microliters, I am going to stop because I don't want to pop the membrane. I'm going to pour it off. Go, little guy. And I'm going to check that. We need 100 microliters to transfer to our plate. Oh yeah, that's plenty. That's beautiful. Okay. And then we do our next one. You can actually see the little, that's the stroma from the red blood cells down at the bottom. That's why it's red down there. All right, that's probably more than enough. But the key is you don't want to go too far. And I'm not even getting to the point where I have like resistance yet, because the beads will physically provide resistance. When you're at that point, you're at a high risk of popping your membrane. Okay, there we go. All right, so at this step, we are going to transfer 100 microliters of our supernatant, which we just poured off into these new tubes. I'm gonna move these out of the way. We're pretty much done with these now. I'm not going to throw them away yet, because say I didn't have 100 microliters in here, I could go back, push it down more, and pour some more out. And we will have a template for you to record where you're putting each of these on, where you're putting each sample on your plate, so that you don't lose track. All right, so we've transferred that. So we're pretty much done with this homolysate, but once again, not throwing anything away. And this is also why I've very clearly labeled all of my tubes. This one I have labeled hemoglobin A1C Supernatant. So that way I can keep track of what's in every tube. All right. So the next part of this is we're actually going to take our homolysate again, and we need to calculate what the total hemoglobin is in each of these samples so that we can get a percentage of our glycated hemoglobin. So for this total hemoglobin part, we are going to pipette 5 mLs of distilled water so that we can dilute our homolysate so it's not super dark like this, because that will be too much absorbance in our spectrophotometer. So 5 mLs of water to each of these tubes that I have labeled total hemoglobin. And all right, so I filled these with 5 mLs of distilled water, and now we are going to do 20 microliters of the homolysate to each of our tubes. So I'm actually going to make sure that these are mixed, because otherwise the stromal will fall to the bottom. There we go. All right. So tiny. So we're going to vortex these. Gonna make a little tornado. Alright, so now we are going to pipette 100 microliters of each of these diluted total hemoglobin samples into our microtiter plate, and we'll read them on the plate reader. I'm doing them in the same order that I had the other ones, so that way I just know that the top 3 are the glycated hemoglobin and the bottom 3 are the total hemoglobin. You could also do them in different columns. You'll have a template so you can write down where you put things. It also helps if you have a white background so you can see where you've pipetted. There we go. All right, now we're going to take this over to the plate reader and read the absorbance values. So this is our plate reader. We have it set to 405 nanometers. An instructor will be manning this when you bring your plate to them, and you'll get a printout of your results. So we've already got it all set up, so it's just as simple right now as clicking OK. And then it's going to suck it in there and read each individual well and report out the absorbance. It actually physically moves the plate over the detector while it's inside. And we have the option of saving it. And we'll save your data, and that will be available to you, but you'll also receive a printout. All right, so the Excel sheet will actually say when it was run, what absorbance it was at, and then it will also have a physical diagram of the plate. And it's also got a nice little heat map thing based on the absorbance. So the darker blue is that it had more absorbance, and the lighter colors is that it had less.